This is the AC Circuits lab from PhET. In this video, I'll be using this virtual lab environment to show you how capacitors respond when I place them in circuits of different configurations. We'll start by looking at what happens to a single capacitor when it's connected to a battery. This device that you see right here, this is a capacitor. And as I close the switch right here, current will begin to flow through the capacitor. And once that happens, the capacitor will charge up, creating a voltage opposite to that of the battery. As this happens, the current through the circuit will gradually decrease, which you will see if you look at this ammeter or current measuring device over here, until the capacitor is fully charged. So let's watch that happen. So what you can see here, once I close that switch, we see some electrons begin to flow out of the negative pole of the battery and into the positive pole. As that happens, we build up some charge on the capacitor. We're seeing negatively charged electrons build up on one plate, positively charged protons, excess positive charges build up on the other side. And then very quickly, that capacitor builds up enough voltage that it opposes the voltage supplied by the battery, and now the current has reduced to zero. When I open that switch, that capacitor retains its charge, and I can use that as a voltage supply in a different type of circuit, which you'll learn about in other videos. So let me now clear the voltage on that capacitor. I've set up 3 identical capacitors with the same capacitance, and they're in what's called a parallel configuration. And it's called that because if I look at my circuit here, I've got each of those capacitors. They're connected to the circuit by wires, and the wires connecting those capacitors to the full circuit are all parallel to one another. What we'll see is similar to before. We've got electrons flowing out of the negative terminal of the battery, flowing towards those capacitors. As those capacitors are building up a voltage differential with a negative and a positive plate, they're fighting the input voltage of the battery. So the current supplied by the battery going through that current measurement device is gradually decreasing as the charge builds up on the capacitors. If you look at those capacitors, now that we've cut the current basically down to zero, you'll notice that the overall charge on each capacitor is identical to what we saw in that single capacitor case. So if you look at the density of the positive and negative charges on those top and bottom plates, you'll see that it's exactly the same for each of these 3 capacitors as it was for the individual capacitor in that single capacitor circuit. We've basically reached zero current at this point, so I'll stop this, rebuild the circuit so we can look at a case of capacitors in series. In this circuit, I have the same battery and same resistor as we saw in the parallel capacitor configuration. The capacitors themselves are all identical. They have the same capacitance of 0.2 farads. So let's see what happens when I close the switch and allow some current to flow through these capacitors. Just like in the parallel case, I see my current, my electrons flowing out of the negative terminal of the battery through my ammeter and then into my capacitors. However, unlike before, the current declined very quickly. And if you look closely, you'll notice that the individual capacitors contain less charge than what we saw in the parallel case. That happened pretty fast, so I'm going to show you that again. Let's watch what happens. The current starts out at about 1 amp, begins to flow through the capacitors charge up, and then already by the time I finish saying this, the current is down to 0. So it declined very, very quickly, and we reached a smaller maximum charge on these capacitors when compared with the parallel ones. On screen right now, you can see a screenshot of one of these identical capacitors from the parallel video, and you can see that the capacitor that was charged in a parallel configuration has a much larger concentration of charges on its positive and negative plates when compared with the capacitors here that were wired up in series. This is because the equivalent capacitance in the series case is much lower, meaning that I store less charge at the same battery voltage when compared with the case of parallel capacitors. Thanks for watching.